Our next speaker is Celeste Barnaby from UT Austin.
Okay. Hi, everyone. I'm Celeste Barnaby, and I'm going to be talking about our paper, Choose, Don't Label, Multiple Choice Query Synthesis for Program Disambiguation. So recent advances in program synthesis and large language models have made it increasingly easy to generate code from high-level intent. You can describe the program you want in natural language, and an LLM can generate code matching that description. However, high-level specifications may be underspecified or open to interpretation, giving rise to multiple plausible solutions that are semantically distinct. To contend with this, you can try checking candidate programs against test cases or input-output examples, but there may still be multiple programs that match these examples but have differing behavior on other untested inputs. So to address this ambiguity, prior work has explored active learning strategies that identify the desired program from a hypothesis space of candidates by asking questions that clarify your intent. This process continues iteratively until there's no remaining ambiguity about your desired program. These approaches, however, predominantly rely on users to provide outputs for concrete inputs, which has two key limitations. First, manual input labeling can be cumbersome and error-prone in structure-rich domains, such as those involving tables or nested data structures. For instance, if you're trying to generate a table transformation program, an active learning system might ask you to perform your desired transformation on an example input table. This can be difficult and time-consuming, and if you make a mistake, the active learner might fail to return your desired program. Second, most existing active learning methods reason over a fixed data set of inputs and therefore only guarantee correctness on those inputs. For instance, suppose we want a program that deduplicates tables by user item pairs. Existing active learning systems may synthesize a program that behaves correctly on a fixed data set of tables, but is not semantically equivalent to the user's intended program. For instance, if all the observed tables happen to contain at most one item per user, like this one, then grouping by user produces the same output as grouping by user item. And as a result, the active learner may incorrectly return a program like this, which deduplicates only by user. If we later want to apply this program to a new table where a user purchases multiple different items, the program no longer matches the user's intent. So here, if the user purchased two unique items, we want an output table that didn't deduplicate anything, but the synthesized program incorrectly merges these purchases together. So to address these limitations, we propose a new active learning paradigm in which, instead of asking users to label concrete inputs, the system generates multiple choice questions about high-level program behavior. So here's an example of a multiple choice query that our approach may generate. This question describes a hypothetical input table and asks what the output table should look like. The user then simply selects the answer corresponding to the intended program behavior. So under the hood, a query corresponds to a logical formula that represents a precondition on the space of inputs, and each answer option represents a logical formula that represents a postcondition on the output of the program. So answering the multiple choice query reduces to selecting which of several Hoare-style specifications represents the user's intent. We can use an LLM to translate these formulas into natural language, and the queries are designed to balance simplicity, meaning that they're easy for a user to interpret and answer, and power, meaning that they prune large portions of the hypothesis space of programs. Because these queries don't rely on concrete inputs, they can reason about wider classes of behavior than existing active learning techniques. So this work has three key contributions. The first is a new active learning framework in which users answer multiple choice queries about high-level program behaviors rather than labeling concrete inputs. The second is an algorithm for generating multiple choice queries that balances informativeness and interpretability. And the third is an implementation of these ideas in an active learning tool called Socrates and an evaluation over 4 synthesis domains. In the next part of the talk, I'll discuss the main components of our query synthesis algorithm. So first, let's formally define a query. In our framework, a query consists of a scenario phi and a set of k answers psi. Intuitively, the scenario describes a precondition on the input, while each answer corresponds to a different postcondition on the program behavior under that input scenario. Further, we require queries to satisfy 2 properties with respect to a hypothesis space of candidate programs. The first is mutual exclusion, meaning that each program satisfies at most one answer choice. And the second is coverage, meaning that every program in the hypothesis space must satisfy at least one answer choice. These two properties ensure that as long as the user's desired program is in the hypothesis space, there's always one correct answer present among the options shown to the user. So at a high level, the query selection problem is to find a query queue that balances two goals. The first is maximizing disambiguation power, meaning that each possible answer should eliminate a large portion of the hypothesis space. And the second is maximizing interpretability, meaning that the user can easily understand and answer the query. We can measure interpretability as the AST sizes of the logical formulas in the query. However, directly solving this problem is prohibitively difficult in practice for a couple of reasons. First, the space of possible queries is too large for exhaustive search to be feasible. And second, optimizing interpretability at the level of the entire query makes it difficult to isolate and control the complexity of individual conditions. So to address these challenges, we use a decomposed formulation where we first select a scenario phi that captures semantically meaningful behavioral distinctions while remaining interpretable. And we then construct simple discriminative answers conditioned on that scenario phi. So first, let's look at how we do step one. Here, our goal is to synthesize a scenario phi that is both informative and interpretable. To do this, we first generate distinguishing constraints for each pair of programs in the hypothesis space. Intuitively, each constraint describes when programs behave differently. A little more formally, given two programs P1 and P2, we want to find conditions alpha such that for any input satisfying alpha, P1 and P2 produce different outputs. We then solve an optimization problem to find a conjunction of constraints that distinguishes many programs simultaneously while penalizing more complex constraints. The resulting condition becomes the scenario of our multiple choice question. Let's walk through an example. So first, we want to generate distinguishing constraints for a single pair of programs. For example, consider these two programs that filter rows from a table. P1 keeps rows whose price is less than 5, while P2 keeps rows whose price is greater than 20. We'd like to find some simple conditions on the input table under which these two programs produce different outputs. We can think of this as an abduction problem where we want to find simple input conditions that explain why programs behave differently. In this example, we can obtain two such constraints. The first states that a row has price less than 5, and under this condition, P1 would keep the row while P2 would filter it. The second states that a row has price greater than 20. Here, P2 would keep this row while P1 would filter it. We repeat this process for each pair of programs in the hypothesis space. So here, let's suppose we have a hypothesis space of 3 programs, and we can generate these sets of distinguishing conditions for each pair of programs. To find a single constraint that distinguishes many pairs of programs, we solve an optimization problem that searches for a satisfiable conjunction of constraints covering as many pairs as possible, while remaining syntactically simple. We show the full formulation of this optimization problem in the paper. Intuitively, it allows us to synthesize scenarios that are highly distinguishable while still being easy for users to understand. In this example, the optimization problem selects the 2 highlighted conditions. These conditions can both be satisfied simultaneously, and their conjunction distinguishes 2 of the 3 program pairs while remaining simple and easy to understand. The conjunction is then simplified to create this scenario of our multiple choice query. Now let's look at how we generate answer choices with respect to the scenario phi. So given a scenario phi, we want to generate answer choices that partition the remaining hypothesis space as evenly as possible. To do this, we first group programs according to their strongest postconditions under phi. Intuitively, programs that behave equivalently in this scenario are placed into the same cluster. However, there may still be many such clusters, so we merge them to produce a smaller number of clusters. And finally, for each merged cluster, we synthesize an answer choice psi that separates that cluster from the others. Intuitively, psi I is a postcondition on program outputs that holds for all behaviors represented by its merged cluster and rules out behaviors from every other cluster while remaining as simple as possible. We've implemented these algorithms in an active learning tool called Socrates. So in the next part of the talk, I'll discuss our evaluation of Socrates. We evaluated Socrates across 4 synthesis domains from prior work. The first is the table transformation domain that we've looked at throughout the talk. The second is a JSON transformation domain. In this setting, the goal is to transform JSON inputs into structured outputs through operations like field extraction and flattening. Our third domain is image editing, where each task specifies a high-level image edit, such as crop all people wearing backpacks. Unlike the 2 previous domains, these tasks are neurosymbolic and require synthesizing programs in a DSL that utilizes vision models for image classification and segmentation. In particular, programs in this DSL combine neural perception, like detecting people and backpacks, with symbolic spatial reasoning over the detected objects. Our fourth domain, image search, involves filtering a subset of images that have a certain property, for instance, images where a bride and groom are standing next to each other. This domain also synthesizes neurosymbolic programs. Importantly, Socrates reasons symbolically about these neural components, allowing us to synthesize correct programs without relying on the accuracy of the underlying neural networks. We compare Socrates against 3 state-of-the-art active learning techniques from prior work. Because no single baseline applies across all our domains, we consider 2 groups of baselines. First, for the symbolic domains, we compare against sample psi and learn psi. Sample psi selects inputs that maximize worst-case pruning power, while learn psi effectively optimizes expected pruning power. For the neurosymbolic domains, we compare against smart label, which is the only prior active learning approach that provides formal correctness guarantees in the presence of neural uncertainty. So in total, we evaluated 157 synthesis tasks. To generate an initial hypothesis space for each task, we first generated 2 input-output examples and synthesized programs consistent with those examples using a synthesis tool, such as an LLM-based agent. Importantly, we ensure that the hypothesis space always contains the ground truth program, along with many other semantically distinct programs. To compare against prior active learning approaches, we also require concrete input spaces for each task. For the image edit and image search domains, we used the same image datasets from prior work. And for the table and JSON domains, we generated synthetic input spaces by sampling inputs from each domain's grammar. So our first research question asks whether Socrates is more accurate than the active learning baselines. So we measured the percentage of benchmarks where the synthesized program is semantically equivalent to the ground truth program. And overall, Socrates solves all of the benchmarks across our domains, while the baselines fail on 14 to 37% of tasks. Our second research question asks whether Socrates' queries are more interpretable than those of the active learning baselines. We conducted a user study comparing our multiple choice queries against the input-output queries used by baselines. And in particular, we asked users to complete active learning tasks, both by answering multiple choice questions with Socrates and by labeling inputs with one of the baseline tools. We measured both response time and answer accuracy across 4 domains. So overall, users answered the multiple choice queries substantially more accurately, achieving 89% accuracy compared to 64% for input-output queries. And additionally, across all domains, users answered multiple choice queries faster on average. Our third research question asks how Socrates' efficiency compares to that of the baselines. Here, this graph shows average total tool runtime in seconds. So overall, Socrates achieves runtime comparable to prior approaches. In the image domains, Socrates is actually faster than the baselines. To better understand the active learning cost, we also evaluate an instant LLM variant that omits the processing time required to translate logical formulas to natural language with an LLM. And here we see that the underlying symbolic reasoning of Socrates is quite efficient and that most of the runtime comes from this LLM processing time. So finally, we return to the motivation behind this work, allowing users to trust that the programs they synthesized actually match their intent. Our key idea is that users shouldn't have to manually label low-level examples in order to establish this trust. Instead, we can ask users high-level questions that are easy to interpret, easy to answer correctly, and better aligned with semantic program behavior. So in this paper, we've introduced a multiple-choice active learning framework for program disambiguation, developed algorithms for synthesizing queries, and implemented these ideas in our tool, Socrates. So thanks for listening, and I'll take questions now.
If I'm understanding the approach correctly, it hangs on the ability to generate the hypothesis space first, understand what's in the hypothesis space in order to come up with scenarios and discriminating questions. When that hypothesis, one of the things that strikes me is that it can be expensive to generate a large hypothesis space in order to do this, and it's also anything that's non-exhaustive, you then have to start making decisions about which things to include in the hypothesis space and which ones to not. And some parts of this feel a little circular, right? But also it seems tractable because a lot of engineers, I think, will do this in their head. They'll kind of sketch out a program in their head when they get the requirements, and they might ask for new questions. How are you handling managing the size of the hypothesis space? And how are you maybe optimizing around not having to generate something that's completely exhaustive in order to do this?
Yeah, that's a good point. So a couple thoughts here. Yeah, so first of all, Socrates is agnostic to the type of synthesizer you use and basically treats it as a black box. So if you're using an LLM-based agent, I think that generating a relatively small set of candidate programs actually isn't that expensive. But in some cases where it is, or where you're using, say, an enumerative-based synthesizer where it's more expensive, in our implementation, we, when generating queries, sample a subset of the hypothesis space and generate an optimal query with respect to that subset. So that allows us to still generate queries efficiently, even as the size of the hypothesis space scales.
Hi, I'm Awil from UIUC. I think this is very good work. My question is, since you're already using LLM agents, have you also considered creating queries and scenarios using them? Because I think contemporary coding agents already do that, and have you compared against them?
So you're suggesting instead of doing this symbolic reasoning at all, we maybe just give the candidate programs?
The questions or the scenarios may not have the properties that you described, but they still may be useful in guiding the search.
Yeah, I think an LLM probably could generate discriminating scenarios from candidate programs. I think here we're really focusing on these guarantees of correctness and establishing user trust that the program they receive is correct. I think future work could potentially integrate AI techniques more in the process of that, but that was our main focus here.
Thank you.
Hi, I'm Aditya from UW-Madison. So I have a question about the active learning paradigm that you're choosing, right? And it's a riff on some of the questions that have already been asked. So you're using active learning to cut down on the hypothesis space by having the sense of contracts and your test cases in mind. Now, there's really also the element of most likely program and things like that you can leverage if you're learning over lots of data. So have you considered that for the active learning model itself to be something where you ask plain English, clarifying questions to the user, forget scenarios, forget all of that, right? I'm suggesting a completely different paper at this point, but seeing as you're advocating for this paradigm, I'm asking if it might be better to ask these questions that might tease out what the user is thinking about. And the hypothesis space can be as large as they please, and you just find the most likely program that is consistent with the clues they've given you so far. There's no need to pin it down exactly, right?
Right, yeah, I think reasoning about which programs are more likely is a really interesting problem, and I think that could also
And you only clarify to that extent, right? There's no need to pin it down completely. You only ask clarifying questions so that you get the most likely program that the user is thinking about.
Right, yeah, I think that's an interesting line of future work and could, yeah, I think that's another instance where like we could have the AI agents like integrated more into the active learning system, and like that could potentially be more efficient, but again, it also risks like having that uncertainty. But yeah, I think that's a good idea.
Okay, let's take the rest of the questions offline.